Okay, so let's look at to this example or problems. So turn to page 342, problem 7.29. Then for this case, we are given an infinitely long line current which position along the z-axis, right? And it has I value of current, and then nearby it has a rectangular loop with length of A and the height of B. So we are going to calculate the magnetic flux that passing through this rectangular loop. Okay, so based on previous lecture, we know that to find the magnetic flux we can simply use these equations. Magnetic flux is equal to integration B dot ds. Alright, so it means that, guys, we need to find the B, which is due to this line current, and also the ds actually taken from this structure. Okay, so let's say I want to take a sample inside this structure, let's say at this point. So you can draw a sample, and let's say this sample has a width of dy because along this y-axis, and then the height about dz. Okay, guys, this is our sample ds from our structure. Okay, so now since this is a very long line current, so we can simply use the H equation that derive from very long line current. That one actually general equation whereby you can find the H is equal to the I over 2 pi r phi directions. Since the I flowing in positive z, so by right the H field must be in positive phi direction, which is counterclockwise, and the r here, guys, actually the distance that perpendicularly measured from the current to the point of interest. Okay, that should be our r, the distance. Okay, so we also know that the B and H can be related to each other by using these equations. The B is equal to mu H or equal to mu R mu naught H. Alright, so since we are dealing with free space environment, so we can simply replace this mu R equal to 1, and which will result in mu naught H. So based on previous result, the H is shown there, so you can simply put here mu naught I over 2 pi r phi. Right, guys, so bear in mind, guys, this B actually the B that flowing along the phi directions, so it exists everywhere, around 2 pi regions, full circular area. So now we are going to look at the B or H field exactly at this point, because this is our area of interest. So we have to find the B that actually passing through these particular positions. So to make it easy, I would like to draw the diagram in 2D. So now we have in 2D of YZ. Now I'm going to draw again in XY plane, which is we look from top view. So let's say this is my plane X Y. So XY plane, so we know that the Z right here actually Z pointing up, pointing out of page, so the Z here will look like a dot, so actually it out of page. So now if you look at from top view, guys, you will see that this line, guys, will look like a dot again. It's just a dot, right? Because the current now flowing in positive Z. So if pointing in negative, you have to draw as a cross, right? Now it's in positive Z, so just draw like a dot. And again, if you look at from top view, you already can see that this line appear, right, from here to here. Is it? So whereby this is your D distance of separations between the current and also the loop. side, and also this is the length of the loop, which is A. Alright, so that's our top view, which is on XY plane. So now let's say this is our sample as drawn up there. This is our sample, right? Now I want to find the B that actually exists at that particular position. So let's draw our H or B field. Let's say that's our field in phi by right. Okay guys, so by right guys, if you look carefully at this diagram, at this particular point, which is perpendicularly from this line current, actually the B not exist in phi. Actually you can take a tangential component, which actually the B, if you notice that the B will exist in that directions. We must take the tangential component, so that's our B actually. Since the B here guys against the X direction, so you can put here the direction become negative X directions, right? So that's the B actually that appear at this particular point. So now let's put inside all this result into this formula. So we know that to find the magnetic flux, alright, the B now actually in mu naught I over 2 pi. Now we have to change the R equal to Y, because actually now we are assuming that this path along the Y axis. So we know that the distance of the sample to this current actually in Y variable, right? In Y, the distance, the Y could be anywhere between this point and that point, so I have to change to Y. Alright, and then now we know that the direction in negative X directions, a dot. So now how do I find the ds? Ds guys can be obtained as shown above here. So since I want to make it in positive flux value, so I have to make it again in same directions, negative X directions, again now dy dz. Okay guys, so make sure you know that this is our value of B naught, right, the magnitude. So this one we have to change, become a negative X direction. Okay, so now let's put the limit of each variable. The z guys will from 0 to B as shown up here, 0 to B, and the y guys, actually the sample here could vary from this point, which is D, until that point, which is D plus A. So your limit actually here, your lower limit become D and your upper limit become D plus A. Alright, so let's proceed to the end. So you can find the magnetic flux finally actually become mu naught I 2 pi, and integrate over z gonna have B, integrate over y gonna have here ln D plus A over D Weber. Okay guys, so this is the value or the expressions of magnetic flux that pass through this rectangular loop. So you can try yourself and make sure you get the same answer as mine. Okay, so thank you and all the best.